Okay, let's pick up where we left off, and we're going to talk about what KEQ or KC or even KP, what are they telling us? So in this example, we have hydrogen iodide decomposing into hydrogen and iodine gas, and you see they're both diatomics. And then we write the KP expression, as you see there, and they found that the value for KP was 0.0184. Alright, so if you think about this value, we need to think about what the meaning of this number is. And that's kind of the key when we're thinking about AP Chemistry. When we see these numbers, what is their meaning? So this number is less than 1. So think about fractions. If the number is less than 1, is your numerator or your denominator greater? If the number is less than 1, that means your denominator is greater. So to say that in a different way, that means the P, or the pressure, of the hydrogen iodine squared is greater than the pressure of these two multiplied together. So what is the hydrogen iodide? It is the reactant. So this K value is telling us that when we get to equilibrium, we are actually still going to have more reactants than we have products, mostly reactants. So depending on whether the K value is greater than 1 or less than 1, it's going to tell us when we reach that equilibrium point, do we have more reactants at that point or more products? Here's another example, still a decomposition, this time with two different gases though, nitrogen and oxygen. Products on the top, reactants on the bottom. We're using concentrations here, so we have brackets. And they found that this value is actually 2,400, or 2.4 times 10 to the third. Now that number is much greater than 1. So if you have a value greater than 1 for a fraction, it means that your denominator is greater. So to say that in a different way, our NO concentration squared is much less than the concentration of N2 and O2 combined. So that means that at equilibrium we have more of this the numerator. I may have said that backwards. But we have more of the numerator, so that means we have more products. So if the K value is greater than 1, it must mean that your numerator is larger, your products. Less than 1, your denominator. Okay, so to summarize that, if K is greater than 10, now we can say greater than 1, but if it's like around 2 or 3, that's still kind of close to 1. So we're trying to broaden it out a little bit more. If it's greater than 10, or 10 to the first power, 1 times 10 to the first power, then we can say that at equilibrium, the system contains mostly products. Another way to say that is the equilibrium lies far to the right. If you think about the reaction, the right-hand side is where the products are. If the equilibrium constant is less than 0.1, again, we're just trying to broaden it out. If it's less than 1 and not close to 1, then it is mostly reactants. Your denominator in your equilibrium constant is going to be larger. And we could also say that the equilibrium lies far to the left, because that's where the reactants are. If the equilibrium constant is around 1, that could be anywhere from like 0.1 up to 10. If it's in that range, then it's kind of in the middle. We have fairly equal amounts of our reactants and our products. Here is an example of a particle representation of a reaction of AB going to A and B. And they say that the container that we're seeing is at equilibrium. The question is the equilibrium constant greater than, less than, or approximately equal to 1? So first of all, let's think about our equilibrium expression. So we would have K equals, then we'd have A and B separately in our numerator, and then that AB molecule in our denominator. Alright, so let's look and see what we seem to have more of. I'm going to circle the AB molecules. 1, just flashing them now. 9, 10, 11, 12, 13, 14, 15, 16, 17. Whoa. So I can already see right there that I have way more AB than I have A and B. So if I have more denominator than I have numerator, then that must mean that K is less than 1. Put another way, if I have more reactants, way more than I have products, then again K is less than 1. So that's the way they could pose that in pictures. They love pictures on the AP exam now, so look out for something like that. You would just kind of count or even just visually assess, do I have more products or more reactants? More products, K is greater than 1. More reactants, K is less than 1. Alright, here we're going to start on some more difficult equilibrium problems. So we're going to be doing some more math. Hopefully some of you will enjoy this. This is kind of a first taste, so follow along the best you can. We'll be doing lots more examples, but make sure you understand the premise and gather any questions that you might have. In this example, we're going to start out with only water gas in a rigid container, and they give us the temperature, and they give us the initial pressure of the water. So some keywords here, just when we're starting. Whenever you see the term initial, that's a really important term, or in the beginning, or you start with. Also, we're dealing with pressure, so we're thinking about Kp, hopefully. And then this pressure, we need to make sure we identify what it's the pressure of. That's the pressure of our water. Okay. What are the partial pressures of each species when the system reaches equilibrium? So currently we're not at equilibrium and we have a pressure of 0.784, and that's the only thing we have is that water. So we know that the water, some of it is going to get used up to make some hydrogen and oxygen. But the question kind of is how much of it is going to make hydrogen and oxygen, and then how much of it will be left when we're done, when we get to equilibrium. The way that we problem solve these equilibrium problems where we have initial values and we're asked about equilibrium values. Okay, so when you see problems where you have initial and equilibrium in the same kind of problem, the same types of words, you want to think about this setup. Okay, and this is called an ICE table. The I stands for your initial values. The C stands for the change in those values as the reaction moves forward. And E stands for your equilibrium values. At the top of this chart, you always put your reaction. So we have the reaction, then the initial values, the change in those values, and the equilibrium. One thing to keep in mind is that you could also call this a rice table, where the R in rice would stand for reaction. So that would remind you to put your reaction at the top. Now in this problem, the only thing they gave me was the initial value for the water, but they did tell me that that was all that was in the container. So I know that the other two were initially 0. There was none there. So notice that I put those values on the I line under their respective elements or compounds. The next thing you do is fill in your change line. Now on your change line, you're going to put a negative for the things that are being used up. In this case, the water is going to be used to make the product because it's the reactant. So we put a negative for the change because its concentration or pressure is going to go down. The products then have positive signs in front of them because they're going to be going up in concentration or pressure. We then use X to show that we don't know what the change is, but we know it's related, and then we relate it by our coefficients. So every time we use 2 water molecules, so 2X, we're going to make 2 hydrogen molecules, so 2X there as well, but we're only going to make 1 oxygen. So we have a coefficient of 1 in front of the oxygen. So that is how we make the change line. From there, you're just going to do math. So you kind of pretend this is like a line in your elementary math, and then you just pull down 0.784 minus 2x. So just write that. 0 plus 2x is 2x. So we write that. 0 plus x is x. So we write that. Okay? So far, so good? All right. Now, we're going to write our equilibrium expression. So we've got products over reactants raised to their coefficient, and we're talking about Kp. So we write our expression using those p's for pressure. Now we're going to plug in our values. Whenever you do an equilibrium expression using K, you have to use your values from your E line, your equilibrium line. So for the H2, we had 2x, so we plug that in for the H2. And it's still squared because that coefficient becomes an exponent. For the oxygen, we just had x. And then for the water, we had 0.784 minus 2x, and then that was squared. Our Kp value was given to us in the problem. So we plug that in for Kp. Right? So we write our expression first. We then look at our table and plug in the values. Don't drop those coefficients though. Be careful with that. And then if they give you the K value, you plug that in. Alright, now going on from here, we've got 2x squared would be 4x squared. Times x makes 4x cubed. Remember to square your number and your letter. So that becomes 4x squared times x, so 4x cubed. Now here, this is looking pretty gnarly, right? If I had to square this bottom term, yikes. That would cause me to have to do the quadratic formula. So here's a shortcut that AP is going to let us use. This is an important one in this star box here. If your KEQ value is less than 1 times 10 to the negative 4th, so if it's 1 times 10 to the negative 4th, negative 5th, negative 6th, so on and so forth, we can usually ignore x's that are added or subtracted. So let me see if I can make this note for you over here. When we say ignore this x, that's going to be x that is added or subtracted. Those are the x's that we can ignore. So we can't ignore these x's up here on the top because they're being multiplied. But this x down here on the bottom, this minus 2x, is being subtracted. So we're going to just negate, is the word we use. We're going to negate that x to where we now have just 0.784 squared. Again, do not lose your exponents as we go through here. Remember our goal, let's keep that in mind, we're trying to find the equilibrium concentration. So we need to find x in order to do that. Alright, so if we back up a step, they don't show you how they solve here. So we're going to square this 0.784 on the bottom and then cross multiply with the 2.0 times 10 to the negative 42. After that, we would divide by 4 and then take the cube root. Okay, so cross multiply, divide by 4, and then take the cube root. You want to make sure that you can do that in your calculator. Okay, so please pause and try that, and make sure you come up with this value for x. Okay, if you don't, jot down, write a question, whatever. This is our value for x. So if that's x, if you look back at your ice table, x is under O2. So that x represents the pressure of O2. Notice that we put the pressure unit on there. We've got to make meaning of this number. X is not the answer, okay? X is helping us find the answer. So from x, we can say, oh, the pressure of O2 is x, so it is 6.75 times 10 to the negative 15th atmospheres, since we're talking about pressure. However, for H2, that was 2x. So 2 times that number, atmospheres. All right, and then what about the other one, the H2O? Well, if you take 0.784 and you subtract 2x, your calculator is still going to say that it's 0.784. Or maybe it'll say 0.78399999999. Essentially, it's still the exact same number. Because x is so small compared to the 0.784, subtracting that 0.784 really doesn't change our value. And that is the reason that we can get rid of x's that are added or subtracted. Because x is normally so small that adding or subtracting x to any number doesn't really change its value. So you see here two checks. Check 1 compares x to our original value, and it was much smaller. And then check 2 plugs in x to our expression to make sure we get the right KP value. Both of these things are solidifying the fact that it's okay to ignore x in these instances. Now, if k is greater than 1 times 10 to the negative 4th, these checks would show us that it's not okay to eliminate x in those instances. But as long as k is less than 1 times 10 to the negative 4, it should be okay to eliminate x. Alright, example 2. Find the equilibrium concentrations, so same kind of question, of all species, so we're looking for those E values again, if 0.194 moles of our reactant is allowed to come to equilibrium. So that's how much we're starting with, and then it comes to equilibrium in a 5.8 liter container, and they give us the temperature. Here we have a KC. So let's remind ourselves, what does the C stand for? C stands for concentration. Is concentration moles? No, concentration is moles per liter. So we're going to have to take these two values and divide them to find the concentration of COCl2. They didn't mention any of our products at the beginning, so we can assume that those are 0. And then they gave us the Kc value. Alright, so if we're looking for equilibrium values, we're thinking about a rice or ice table. But first, as I mentioned, we need to calculate the concentration in moles per liter. So moles divided by liters, there's my concentration of my reactant. And that is before the reaction takes place. So here's my ice table. And there's my concentration of my reactant. And the other two I'm assuming to be 0, since the reaction has not occurred yet. On my change line, these all have coefficients of 1. So I've got minus x for my reactant and plus x for my products. Then I'm going to just bring that math down, and there's my equilibrium line. So if I can figure out x, then I can figure out the equilibrium concentration of all these species. So I'm going to write the equilibrium expression, and here I'm using brackets because I have a Kc value, or a concentration value. And then I'll plug in my x's and such from my E line in my chart. So it'll look like that, x and x for the COCl2, which equals x squared. Or excuse me, for the CO and the Cl2. And then for the COCl2, for that compound, that was 3.3 times 10 to the negative 2. If I look at my K value, it is much less than 10 to the negative 4th. It's 10 to the negative 38. So I can negate this x that is subtracted. None of these had coefficients, so I'm not like squaring anything, but x times x would equal x squared, and then I'll just pull down my 3.3 times 10 to the negative 2 without the minus x. So here I'm solving for x, so I would cross multiply these two, and then I would just take the square root to find x. So there's my x value. Notice the unit here. I was dealing with Kc, which is concentration, so my unit is molarity, capital M. That x represents the concentration of both my products, so the concentration of CO and Cl2, and for my reactant, it would be 3.32 times 10 to the negative 2 minus that. But again, if you put that in your calculator, it wouldn't register any change in the concentration. So if you look, the value of x is so much smaller than your original, it would have no effect. And if you plug it back in, you'll get the same Kc value again. So that is a good check that you can eliminate x. All right. An example of an equilibrium situation that is important in terms of world history, especially from World War I, is this COCl2 that we just looked at. And so you see the gas reaction at the top, and then you see the reaction of that same gas with water at the bottom. One of those is reversible, and one of them is not. If you're interested in learning more about this, I would love to discuss this reaction more in class, if you want to just come with a few facts about that to get that conversation jump started.